Okay, so let's get started. So in the previous lecture, I introduced this idea of what model checking is, and in particular, we sort of discussed that we need two ingredients in order to do model checking. The first one is this mathematical object, which is a transition system, and so we spent the entire lecture understanding what a transition system is and what are its elements which comprise or make up a transition system. It's just a tuple with these 6 objects, and I hope you recall that there's the notion of states or locations and initial state. There's an action or input space of this transition system. So those are the first 3. Then there is a transition relation, which is a set of all possible transitions. And each transition relation itself is of the form source, action, and sort of destination. And then there is something called atomic propositions, which are things of interest to the model checker or the developer, right? So these are very small statements which are either true or false, and we would want to know where in the transition system which atomic proposition is true or false, and that relation is governed by the labeling function L. And so we saw an example of this, and then in doing so, we also discussed that what we are interested in is, in long term, we want to know what properties or atomic propositions occur in different paths traversed in the transition system. So we had more definitions of what a path is. A path is just an infinite sequence of states. And so what induces a path? If you get inputs from the, say, outside of this transition system, so the ABCs of your figure, this set of inputs is called a word, or a sequence of inputs, because inputs themselves are sometimes called alphabets. And so input induces a path, or a word induces a path. And then when traversing a path, you actually accumulate or log down which propositions were true where. And so what you end up with is getting a trace, which is of the interest to us, because that's where the information about some behavior that we are interested in as a designer lies, in the trace of the system. And so we saw examples of that. I think we wrapped up our discussion on this example where we already are doing this manual exercise of what model checking is supposed to do, right? We are given some specifications. So these 3 statements are what you can call specifications. And you are interested in figuring out whether your transition system or your model satisfies these specifications. And then we discussed that in this example, for instance, if it does not satisfy the specification, then you have to produce a counter example. And one example is enough to say that the system doesn't satisfy a specification. And so what I was trying to wrap up in the previous lecture, the point I was trying to make is, like, if you look at the middle specification here, which is M is always followed by a Q, there is some ambiguity here, because it doesn't specify whether M is immediately followed by Q, or M is at some point in the future followed by Q. And so this sort of ambiguity is not allowed in model checking, right? Because you need to really give, when you're talking about giving a guarantee, it really matters what you are trying to specify, or what certification from your system do you desire. And so to avoid this ambiguous sort of English language syntax, we will learn a new language, and that's what we will do today. We will learn a new language of temporal logic, or linear temporal logic, right? So as the name implies, it's based upon the principles of logic, where we want to focus on defining some operators or a grammar of this language, if you will, that will tell you what you can specify and what you cannot specify in this language. And so that's the whole objective of this lecture, to literally learn a new language. If you haven't seen before, don't worry. I will introduce this from the ground up. Okay? So we want this language to be able to describe our requirements to a model checker, so that given this requirement and the transition system, the model checker can return an answer, or it can return a counter example. Either of those 2 always occurs. So linear temporal logic is nothing but this language of describing things. And the way it differs from, say, Boolean logic, which I'm sure you have seen, and you're all familiar with, but we'll do a quick recap of that in just a second. It's a way to essentially compose some requirements based on using these small atomic propositions, right? So far, we have seen that in our trace, we only worry about whether P is true, at some point, or we are trying to look at very simple statements. But what you want is to be able to compose a real sort of verbal or English language requirement into the equivalent mathematical linear temporal logic formula. And so the basis of this formula is still going to be our atomic propositions. The only difference is that we will introduce some new temporal operators. This is where the word temporal comes in LTL. Right? So if you think about it, even before I show you the actual stuff, in Boolean logic you have and, or, and not. Those are mainly the three which are used, and you can derive other stuff from those three. But there is no notion of time in Boolean logic, right? So I can say I want P and Q to be true, but I cannot really say I want P and Q to be true in 5 steps from now using Boolean logic. So that's why we will use Boolean logic and augment that with some temporal operators that I will teach you today, and that will form sort of this dictionary or grammar for linear temporal logic. Okay, so here are some things that we cannot specify perhaps in Boolean logic, right? So we want to, or maybe we can, and if there's a notion of time, we cannot. So like the first one says that if you have a multiprocessor system, you may want to have a requirement in your model of that system that no two processors can share the same sort of cache line when they are writing code at that time, right? So that's a English language requirement, and we would want the logical equivalent of that. So we would have maybe a variable which says the cache line belongs to processor 1 or processor 2. And then we can also say another flag which says whether you are writing or reading from the cache line. And you can compose some logical statement that could be the equivalent of what is shown here. And the other one is also something that you see a lot in computing and signaling in general, that it says that if someone is requesting something, then it must be granted at some point. That's the gist of it. And likewise, the last one is that every request signal must receive and acknowledge, and the request should persist or stay asserted until the acknowledge is received, right? So even when we read this, there are these verbs over here which are telling us until. Until is already like a temporal property. It's not like a logical property, right? So we cannot use Boolean logic to represent each of these requirements as just a simple logical formula. We need the notion of time or sequence, rather. You should think in terms of sequences, not necessarily in clock time. And so that's what you have to do. And this is where LTL comes in. So simply put, linear temporal logic is nothing but Boolean logic with 2 special operators. One operator is called next, and the other operator is called until. And I'll tell you exactly what these operators are defined as. And don't worry about the stuff on the bottom slide. We'll revisit it once we see examples. The way we will try to wrap our heads around linear temporal logic is I'll show you a lot of examples to build your intuition, and then I'll describe the mathematical notion of it, like we always do. Okay, so before we do that, let's just do a quick refresher of what Boolean logic is. This is the simplest case. There's an operator called not. So if you have a proposition P, which is true or false, the not of P is just the inverse of that, so you all know this. Also, we have an operator called AND in Boolean logic, which is true only when both P and Q are true, otherwise it's always false, right? That's the AND operator. OR operator is false only when both are false, otherwise it's always true. That's the OR operator, and you can very easily fill the truth table, as they call this, of these operations. And then there's an operator called implies as well. Who has seen this before? Okay, so implies is, you can actually compose implies using and, or, and not operations. But the way to think of P implies Q is, if P, then Q. Or we are trying to look at the preposition or the kind of the assumption P and trying to conclude whether Q is going to be true or false. So let's look at the truth table first and then see how we can explain some of these values. So let's look at the first one, right? So the way to read it is a true proposition can lead to a true conclusion. Therefore, P implies Q is true when both P and Q are true. Okay, so if P then Q can be verbally expressed as a true, what is the relationship between a proposition and what you are inferring from that proposition, right? So if P is true, a true proposition will lead to a true conclusion. Therefore, P implies Q is true when both P and Q are true. What's the second one? You cannot conclude something false from a true proposition. Therefore, P implies Q is false when P is true but Q is false. And the bottom two ones essentially say that you can conclude anything you want if your proposition is false. Therefore, P implies true is always true no matter what, if your P is false. It doesn't depend upon the value of Q. Right? So if you haven't seen before, I've left this here so that you can revisit this part of the lecture. But essentially, P implies Q is a special operator that you can compose. So what do I mean by compose? Let me explain that. If this is your input and to the implies operation, and these are the outputs we want to generate in our truth table, we can create a function which only uses negation and, not even or for that matter, that can generate this output truth table, right? So this is just a high-level Boolean operator which can be built from low-level Boolean operators, right? So we may not have seen this, or it may have been some time, but that's what implies mean. If P, then Q. And what is P and what is Q? We don't care, but we care about whether P is true and Q is true. And based on that, what can we say about P implies Q, whether that is true or false itself? So now we go back, right? So given these Boolean operators, we have two special operators. One is called next, denoted usually by a X. There's another symbol. I'll show you that towards the end of the lecture. And then another temporal operator called U, which denotes until. So before I explain the math, let me give you some examples of how this works, right? So shown here on the slide are some examples of traces from some transition system. We don't, at this point, care about what the number of states are, because we've already started thinking in terms of the trace of the transition system. So I actually don't really care where this trace is coming from. This is just the runtime sequence of how propositions were getting true as you were transitioning based on some operation of your model. This bottom arrow, which is hard to see, but there exists this bottom arrow on the first state, and these are different traces. They're not the same trace, of course. This denotes time, where time is. And so this arrow denotes that the first state of this trace is the time that we are talking about as the time being now, right? So this is the initial time that we will look at when we look at this trace. We will look at the first element of this trace as something which is true right now when we want to check the LTL semantic, or when we want to talk about the LTL semantic. So what is this semantic, right? Let's look at the first one, the topmost one. So if I just say a proposition P, I'm not doing any logical operators on P. P is atomic proposition. So I can ask, does this trace, the topmost one, satisfy the LTL formula P? And what you would read that as is, since I haven't, I haven't really specified where or when do I want P to be true. If you just specify the atomic proposition itself, you read this as, is P true now for my system, where now is defined as the very first state by default. Okay, so indeed, this transition system, what is this system itself? We have a trace where we have P is true, and then actually I haven't specified what else is true. It could be anything. It could be Q or ST, or it could be P as well. So the question that we have to always ask is, given a LTL expression, the simplest LTL expression is just the atomic proposition itself, without any composition with any operator. So I can say, is P true for my system? And I read that as, is P true now? Now is the keyword, because I haven't specified any temporal operator with P. And so I look at the system, I look at the first state, or what is happening now, which is this arrow, and indeed P is true for this trace. Let's look at the next one, which is very interesting. The notation GP, G is an operator now, and it's notated by G as the capital G alphabet in LTL. What G means is globally, or much simpler, GP means P should be always true in my trace. Globally, P remains true. Other stuff can also be true and go back and forth, but does my trace satisfy the property G of P? Indeed it does, right? P is always true in this very simple trace because that's the only atomic proposition we are looking at. F of P is, F comes from the fact that you are talking about finally P is true, or in the future P is true, or more simply, eventually in my infinite trace, I want P to be true. Or the question is, does this trace satisfy this property that eventually P will be true? And yes, indeed, the example has been chosen that we don't care what is true right now. We want P to occur, which will satisfy that in the future P is true. So F of P is satisfied by this trace. So I see some blank faces. So someone can help me. Why don't you try and give the next one a shot? What do you think XP is trying to ask or specify based on the picture? Yep. Exactly, right? So X is the next operator. So unlike P, where we didn't have any operator, now I say XP, where X means that is P going to be true in the next trace element? That's what XP is. And so does this trace satisfy XP? Yes, it does, right? Because now we don't care what is true, but P is true at the next state. Therefore, XP is satisfied by this trace. So similarly, can someone else now try to explain what P, U, Q could be asking or describing? Yeah? Yeah, right? So very simply, P until Q means we must see a Q at some point, and until that point, from now onwards, P must always be true. That's what P until Q is, and that's what the picture is also, right? So it doesn't mean that every P will get its own Q, by the way. That's not what it means, right? So there's a distinction there. It only means P until Q is true if I see a Q in my trace. That's my first requirement. And until I see, from now until I see that Q, P has always remained true, and therefore P until Q is satisfied by this trace. Everybody with me so far? Okay, so these are examples of semantics. The last one is, again, we won't use the before operator for good reason. I'll tell you that later, but let me at least tell the definition since it's here. P before Q says that I must see a Q, and P must have occurred at least once before that. So it's kind of a softer version of P until Q. P until Q says P must always remain true until I see a Q. P before Q says if I see a Q, the trace satisfies P before Q if P must have occurred at least once before a Q. And so similarly, it doesn't say anything about that every Q must get its own unique P. That's not what the statement is, right? So even this trace actually satisfies P before Q, because by definition, P has occurred at least once before Q has occurred. So we use these expressions, the ones which are shown in this green/teal color, and we call these expressions as our LTL formulas, right? We are using the notion of time. Where is time coming in? With operators like next, until, always, eventually, before. They are all temporal operators, unlike Boolean logic. So now let me mathematically tell you what LTL is, and it'll be very clear based on an example. LTL is a language, and like any other language, just like English or any other language, there are some rules and method to the madness of what you can express in that language. The rules of LTL are very simple. They are listed here on the bottom of the slide. So let me go over this one at a time on how do you interpret these rules. So let's start from the left-hand side. If you see the expression, the statement true, literally written as true, true is like the empty matrix default state of LTL world. Okay, that's the analogy. True is satisfied everywhere. It doesn't matter which proposition is actually true or false. True is the default state of the LTL world. And so any trace, I don't care whether the first bracket is empty as well, any trace will satisfy true, just by definition, because true is true everywhere, literally. I know it's a little bit meta-philosophical point here, but it's required for the language to work. The expression true is part of the LTL formula or language. So you can write and use this expression when you specify LTL logics, the expression true itself. The second one we sort of already looked at, right? So if we have a atomic proposition, so P belongs to the set of atomic propositions AP, then if I just specify P1, that's a valid LTL formula. It's part of the dictionary. It's allowed. It's allowed for you to say that, does my trace satisfy just P? And we just saw an example of that actually in the previous slide. In this example, both of these are valid LTL formulas, right? I can say, does this trace satisfy P1? And the answer is yes, because P1 is true now. Does this trace satisfy P2? Same logic. P2 is also true now. How do we know they are true? Because we are given this labeling function, or the trace is telling us what is true when. Okay? So subtext here, what do I mean when I say something is valid LTL and not valid LTL? Valid linear temporal logic means that a model checker will allow you to write that expression, or you can do model checking with that expression rather. An invalid LTL formula cannot be model checked. I mean, you can write any symbol you want, nobody's preventing you, but if that symbol doesn't adhere to the rules of the LTL dictionary or grammar, then it's not a valid LTL formula. And so this stuff in the pink sort of text box on the bottom of the slide is telling you what is valid or invalid in terms of a LTL formula. So we've seen that true is valid, just the atomic proposition is also valid. The next one is also very simple. If you have an LTL formula phi1 and phi2, then phi1 and phi2 is also a valid LTL formula. Okay, very, very straightforward. So in that example up top, I can also say P1 and P2. Can you tell me if this trace satisfies P1 and P2? Indeed, it does. Okay, that's just an example. But the point is not whether this satisfies or not. The point is this is a valid LTL formula because it's allowed in the grammar. So far so good. Let's keep going. The next part of the grammar is, if phi1 is a valid LTL formula, then not phi1 is also valid. Okay, so I have another example where I can ask whether not P1, where P1 is my phi1, P1 is a valid LTL formula, so not P1 is also valid, and then I can ask whether this trace satisfies not P1. And the answer is again yes, because the first element of the trace is not P1. So these are the easy ones, or the ones that are easy to understand. If you have a LTL formula phi, then you can use the operator x phi. So now we are talking about this part of the grammar. So if phi is a valid LTL formula, then x phi is also valid. So I can ask, does this trace satisfy xp1? What's the answer? Does the trace or the second trace satisfy xp1? Yes or no? It does, right? I hope everybody is on board. It does, because when we say x, we are talking about the next state, and P1 is true. What about this? Does this trace satisfy this formula? Let me first ask you whether this is a valid LTL formula. So how do you think about this? Right? You'll have questions of the form, is this expression a valid LTL? What you would want to do is, you want to say that, well, this is a valid LTL because negation of a LTL is valid. Then this is a valid LTL. Therefore, x of this is also a valid LTL. Right? So this is a very simple example, but in your homework, this won't be as simple, right? So that, but I'm just telling you how do you prove whether this is a valid LTL. You have to decompose that formula into a set of valid LTL formulas. That's how you show something is valid LTL. So I didn't hear the answer. Is this true or not? Does the trace satisfy this? Yeah, it does, right? So let's break it down. How do you know? Now we are again jumping from LTL directly into this manual model checking, right? Later a tool will spit this answer automatically, but let's see how do you convince ourselves. So whenever we have the next operator, it's very useful to start looking at not the now state, but the next state itself. And so what this is saying is at the next state, P1 should be true and not P2 should also be satisfied. So at this state, indeed P1 is true and P2 is not true. Otherwise, we would have said P1, P2. Therefore, it is satisfied. What about this formula? Let me write a formula here. X of not P1. Does this trace satisfy this formula? First, let's convince ourselves this is a valid LTL expression. It is a valid LTL expression because not of phi1 is valid. Next of phi1 is, let's say, phi2 is valid, and you can keep using as many next operators as you want. So does the trace satisfy this? It does. Again, the 3 x's already tell me that I care about next. I care about this state. And then the parentheses tell me that P1 should not be true, therefore this trace satisfies this LTL formula. Okay, so that's how you use the next operator in conjunction with the previous definitions of and, not, and a single proposition, and you'll later see true as well. So now we are only left with the last one. We've already seen an example of that. You want to say P1 until P2 is a valid LTL formula, or in general, if phi1 and phi2 are valid LTL formulas, then phi1 until phi2 is also a valid LTL expression. That's it. These are the rules of LTL, very straightforward. So using these rules, given a formula, you can first establish whether or not that is a valid LTL formula or expression. And given it's a valid expression and a trace, you can do model checking, which I haven't explained yet, but that's what's coming later. So is the semantics or the grammar of LTL understood? Or you have any questions? I can pause for some questions here. Okay, so it's just, I think, 6 things which have to be true for this to be LTL, or they have to be derived from these 6 elements. Cool, so the rest of the lecture is, believe it or not, just examples, so that we'll do this again and again and again, so you get tired of it, but then that's the only way we do our own, like I say, reinforcement learning. Okay, so let's jump into it. The way you have to answer now is, don't yell it out, raise your hand, I'll call upon you. First, you have to tell me in English language what is the LTL trying to express, and then tell me whether the trace satisfies the expression which is shown here. So let's do the first one. Who wants to give it a shot? Yeah, what is the, first tell me what are we trying to check, or what is the expression? Very good. And is it satisfied? It is satisfied, right? So let me repeat it. The expression, it's pretty straightforward, is saying, let's look at the innermost stuff and then start going outwards, which is unlike how we deal with the X operator. In most of the cases, you would actually deal with inside to out, or inner to outwards, rather than outwards to in. So the inner expression is just P1 until P2, which is a valid LTL formula. So for P1 until P2 to be true, we have to first see P2. Okay, we have our P2 here. And if P1 until P2 was true, then all of these had to be P1. But our formula actually is the negation of a LTL formula, which is a valid formula itself. Therefore, indeed, this trace satisfies that it is not the case that P1 holds until P2. With me? Good. Let's look at another example. Same drill. Someone tells me what's the English expression we are trying to check, and then the other person or the same person tells me whether this is satisfied or not. So who wants to give a shot at what the expression is? Yeah? Okay, so you literally read it out, which is fine. Now tell me, which is fine, this is the correct explanation, but tell me now if it's satisfied or not. It is, okay? Everybody sees that? So let's again use the same trick as before. It's not really a trick, but a method rather. We start from inside to outside, right? So let's resolve this part, because then it will become phi1 until phi2, and we can reason about that. So what is phi2? Phi2 itself is a form of phi1 and phi2, or you can keep going 3 and 4. So let's look at this condition, P2 and next P3. Where in our trace does this condition occur? Because for something until something to be true, we first have to locate that until, or the expression that follows the until operator. So as you can see, here is where this is true. So P2 and next P3 says that P2 is true, and then in the next state, P3 is true. So indeed, we have this part does occur in my trace, so I can then proceed to explore whether it is the case that before that happens, P1 always remains true. So before this part occurs, where P2 and next P3 is true, indeed, indeed it is the case that P1 is always true. Okay, the first three elements do contain P1, so this is satisfied by my trace. Everybody gets it? Good. Let's keep going. All right, someone who hasn't spoken yet. What are we trying to check? Start from the inside to outside and say it in English. Yeah. Is that how you would infer it, or is there a better way to phrase? You are correct again because you simply read it out, but what's a better phrase? Like if you are explaining it to someone who hasn't taken an LTL class, how would you say? Very good, right? So we want P1 to not be true until P2, but we want this statement to hold true starting from the next statement. Correct? So let's do our same thing. In this case, however, our first operator is x. So like I said before, it's better when you encounter a x to already start jumping onto the next state. So all of the story that follows x has to apply from this point onwards. So what is that story? It says not P1 until P2. So starting at this point, do we actually ever see a P2? Yes, we see it here. And until that point, starting from here, is it not P1? Yes, there is no P1 in these two states. Hence, our trace satisfies this LTL formula, which is a valid expression as well, right? You can also always ask that question, whether this is a valid thing to check in the first place. Let's do one more, and we'll do a lot of these so that this becomes a second nature to you. True until P1. Does this trace satisfy this expression? True until P1. Can someone tell me what is this expression equivalent to? What are we actually saying in plain English about P1? How would you say it in terms of an operator that we've just seen in the previous examples? Well, just until P1 is not a valid expression. You need phi1 until phi2. Yeah? Very good. True until P1, I hypothesize or state, is the same thing as saying eventually P1. Okay? Let's put that as a side. Just first look at why this is true. True until P1 says that I should see a P1 in my trace. That's the requirement of until, which is here. And actually, I don't care what is true before that. Or true is always satisfied at every location. So therefore, this trace satisfies true until P1. So an equivalent way to express the same thing is FP1, right? So P1, eventually P1 should occur. If the trace satisfies true until P1, it will also satisfy eventually P1. which illustrates the point that these high order functions of always P1 or eventually P1 are valid LTL formulas because they can be decomposed out of the grammar. Okay? So in the grammar, there was no G and F. G was always and F was eventually. And there was before as well. The grammar is only true, next, negation, and all that. And so we can decompose those with this as well, right? So is it clear why true until P1 is eventually P1? It's the same thing? Good. So now tell me, decompose globally P1 into the LTL language. That's our next exercise. So I have my pen ready. You can give me some suggestions, and then we'll go through all of those suggestions on what do you think, how can we write globally P1 or always P1 in terms of the basic LTL elements? Yeah, give me a suggestion, yeah. P1 until not true, okay. We'll come back to all of these. I need more suggestions first. Don't think about what he has suggested. Just tell me what you are thinking.
What about P1 implies next P1?
Interesting. So P1 implies this. Okay. Are there more? Don't think about again what exists here. Just try to see how can you express always P1. P1 must always hold true using basic LTL. It's okay. You can be wrong. It's fine. This is a very low risk question as always. P1 until P1. Okay, so let's look at that. Keep going. Any more ideas? Come on, we can do better than 3. Look, okay, slow down. Okay, let me write it down. So you said, I heard true until not P1, and then there was more stuff? Okay, so you want to negate the entire expression? Oh, okay, so this. Okay, we'll take a look at that too. Maybe one more. Let's at least have one more. So we consume some time in this lecture. No, I'm kidding. Yeah, give it a shot. Always P1. So we just saw that FP1 is true until P1. So you can use this as reference to think about what is always P1. Give me one more, even if it's wrong. Because every incorrect one is an opportunity to learn why it's incorrect.
True until not P1.
Oh, so you want the same thing, but you don't want to negate it. Yeah. Okay. So one of them has to work, right? Because either this is true or the negation is true. Okay, so these are good examples. Let me start with ones which may fail, right? So let's look at a trace, P1, 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 and then Q forever. This is my trace. Does this trace satisfy this expression, P1 until P1? It does, right? Because P1 is true until P1 is true. But does it satisfy always P1? No, it does not, because Q is true always. Okay, so this one was a good attempt, but it didn't work. Same goes for the one on top. Does this trace satisfy P1 implies next P1? If P1 is true now, it implies that P1 is true at the next step. Does this trace satisfy that? Because what is the next operator? This is telling me to look at the now position, and this is telling me to look at the next position. So indeed, it does satisfy P1 implies next P1, but it doesn't say anything about what happens after that. So it's not equivalent to saying always P1. And this is an opportunity to get used to this way of thinking of, I'm always going to think in terms of counterexamples. It's very easy to find traces which satisfy your formula, but you only need to find the one example which does not. Okay, so let's look at the other one. So let's look at this one. True until not P1. So I would give you a trace which is Q plus. And Q plus satisfies this formula. Because what is Q plus, if you have forgotten or if it's not clear? Q plus is a series of infinite Qs. So a trace which is a series of infinite Qs satisfies true until not P1. Because each of these are not P1s. So, but this does not satisfy always P1. So, this can't be the expression for always P1. Let's look at this one here. Well, what is the problem of this expression? There's not really a problem, but we haven't really defined what not true is. Okay, so we know that not true is false, but in the LTL semantics, false is not part of the dictionary. Okay, so in spirit, you can think of what this is trying to say is, I will never experience a state where not true is true. Okay, does that make sense? I know this is becoming a buzzword bingo at this point, but I hope it's logical. Right, so true is true always. The expression true is always true. So we will never actually reach a state where not true is true. So what we want to say is P1 should hold until this non-existent state, always. So if a trace satisfies this formula, all it is saying is P1 must continuously hold until the expression on the other side of this until operator becomes true, but the expression on the other side will never become true. So P1 until not true is equivalent actually to always P1, because you'll never reach a state where P1 won't be true if your trace satisfies P1 until not true. In fact, this expression, let's call it expression A, is exactly the same as expression B. I'll show you why. Okay, so let's look at this expression first. We want to say we don't care what is true until we don't see a P1. Okay, that's what the inner expression is. In other words, we are saying if a trace, forget about this negation for a second. Okay, so forget about this for a second, just look at this one. If a trace satisfies this expression, true until not P1, all it is saying is that at some point you should not see P1. Because look, what is true until phi1? It's saying eventually you will see phi1. So true until not P1 says eventually you will see not P1. Good so far? But the negation outside is brilliant because it says we will never want this to happen. We will never want to not see P1, which means you should always see P1. So I'll give you some time to let this marinate. It's all a matter of interpreting symbols at this point, but the way you derive or reason is the key sort of principle here, right? So several things that you must learn is, given some formula, the way to say whether that is a correct answer or not is self-correction. If you can produce a counterexample, the grader will give you full marks, okay? Because you have shown the counterexample where the formula doesn't hold. But how do you show whether something is actually correct? You have to break it down in terms of how I was breaking it down, right? So let's look at the expression B again. This expression is of the form negation of phi2, so it's valid, where phi2 is of the form phi 3 until phi 4, and phi 4 is of the form not of phi 5. So first of all, this is a valid expression. So we look at inwards to outwards. Let's look at this part, phi 3 until phi 4. If a trace satisfies the fact that true holds until not P1 holds, my first claim is that this is the same as saying eventually not P1 holds, because that's the definition of eventually. True until something is eventually something. So the inner part of this is eventually not P1. And it must never be the case that eventually P1 never occurs. Therefore, P1 must always be true for a trace to satisfy not f of not P1. So is it clear how we can now express GP1 in terms of our basic operators of true, P1, and negation? This is also true, but we have to deal with this idea of something that can never occur. So someone can actually say this is not true because for P until Q to be true, Q must occur at 1 at some point, right? So this definition is kind of finding a loophole in that idea, but this one is more correct. It must never be the case that eventually P1 becomes not true. Therefore, this is equivalent to always P1. Okay, so you see how precise we have to be when talking about LTL, right? That's the whole reason, because it's all logical. There is no room for any other interpretations. Yes? Yeah.
So for the second, for
This one?
I don't see like how that doesn't match the because saying P1 implies that the next one is P1.
P1 implies that the next one is P1. My counter example is P1, comma P1, comma P1, comma Q plus.
But then when you transition from P1 to Q, like
No. Why would you get to this point in the first place? Is there a temporal operator on the first P? If not, you are looking at now. Okay? So we are only talking about this P1 when I say P1. P1 implies next P1 means P1 is true, next P1 is P1. Therefore, because of just even these first two, this trace satisfies this formula. I know what you are trying to say. You are trying to say that this formula is not satisfied at this part of the trace. But we never are checking this part because we haven't specified any temporal operator on our first proposition, atomic proposition, right? So that's why it wasn't true. Okay, so these are, I think, the same ones. So we just saw that eventually is true until P1, and then this was exactly what was sort of proposed, right? So you can think of this as f of not P1. It's the same thing. And then, just for completeness, we won't really deal with this part of LTL. I'm showing you here that even the OR operator, phi 1 or phi 2, you might be wondering that I said it's Boolean logic plus other stuff. Where is OR in the Boolean logic? Well, this is news to you that OR is also just a composition of negation and ANDs. Okay, yes? Yeah, you can think of it as that as well. Okay. The point is that many of these operators, even the implies operator, can be derived in terms of not and or, but or itself can be derived in terms of negations and and. So all of them are valid LTL. It's just that, you know, for brevity, we don't want to keep writing this expression for or. So you can derive high-level useful formula from the dictionary of LTL. It's very, very rich. Already you can see, let me digress a little bit. Why would this be useful? Because we can say things like, well, the pacemaker, for it to pace, something must always have been true for it to pace. Right? So we are not fully abandoning or disconnecting our module. I know we are into LTL right now, but you can see how this would be useful. You can say that until I see a V sense, this must have always hold, or eventually the pacemaker will intervene if this was to hold true right now. So now I can come back to the slide which existed before. LTL is nothing. This is just a recap of all of this. It's a Boolean logic plus some temporal operators. So every atomic proposition is part of LTL. Not phi1 is part of LTL. Or and are also valid formulas because or is just dependent on the previous two. And the two new ones are next phi1 and phi1 until phi2. That's all what linear temporal logic is. But this is a great example where complexity can be distilled down as a combination of very, very simple elements. And that's what you will actually learn in this module. So this is more of a public service announcement that in literature, also probably in the assignment, sometimes these symbols exist. So G is sometimes represented by the square, eventually is represented by a diamond, and next is just this circle. So I just don't want you to be confused that this doesn't look like what we discussed, okay? So let us look at some examples of why do we care. Okay, I gave you some intuition on how it maps to the heart, but this is a rich mathematical framework which let's try to grasp what kind of interesting things can we specify using LTL. Right? So let's look at the first one, which says G of not P, which can be interpreted as G is globally or always something should not hold. And in LTL, this is called an invariant. Why is it invariant? Because it's true forever. It's not varying from how the transition system operates. And you'll see an example of this is we can specify safety properties using invariants. So for example, I can say always it must be the case that the temperature of a nuclear reactor is less than 1,000. Okay? And no matter what happens, this must not be violated by my reactor model, mathematical model, or transition system. And this is an invariant property because it's globally true. The next one is interesting. Who can kind of interpret what the next one is saying? Give me like a English expression, human understandable English expression of what is this response property. The response kind of gives it away actually, but still. Go inwards to outwards again.
Q will always eventually follow a P.
Very good. It means, let's look at the inside bracket first. P implies eventually Q means if we see a P, eventually we will see a Q. And this must always be the case. So whenever we see a P, it will eventually be followed by a Q. And that can be interpreted as a response as if a processor job is requesting access to the CPU, eventually it will be granted. And this must always be the case. So every request must be eventually accepted for some system that you are modeling. And let's do the last one. And then we are close to wrapping up the lecture today. So what's the sort of expression in English for the last one? Yeah. Is it only talking about eventualness, or there's a doesn't the implies what? Okay, why don't we step back and restart? What do you think is the expression for this formula? What is it trying to say? You will always eventually see a P, and then what will happen? Correct, right? So that's correct. This literally, if we read out, replace G by globally and F by eventually, this says it always we will eventually see a P in the trace, and when that happens, always we will eventually see a Q. So kind of similar to the top one, but we have this requirement of always and eventually on both P and Q. Yeah?
But if it's, I mean, the first part of that expression always varies to true. I mean, you will always eventually see.
No, if there is no implies, then this is not even a, I would say, valid LTL formula. What does it mean, GFP, GFQ? You need an implies here, right? You need a proposition to be true before the conclusion can become true. Yes?
Since this is an imply statement, isn't there something like if involved in it? Like if it's
Yeah, so correct. So there is an if, right? So we are not yet talking about whether or not a trace will satisfy this. That's where the if comes. We are just simply saying, in plain English, what are we even trying to ask the trace to satisfy? And you are right. We are trying to ask it to satisfy that always eventually you must see a P, which would imply that always eventually it must be followed by a Q. And now let me make all of that jargon precise by saying that this is the same thing as saying P and Q will occur infinitely often. In fact, I can even say they will occur equally often. This is the same thing as saying that. GFP implies GFQ is the same as saying that both P and Q occur equally infinitely often in my trace. So let's break that down. Why? Because when I talk about always P and always eventually P, always eventually Q, I'm already, our trace, remember, is an infinite, a set of propositions. So if every eventual P has to be followed by every eventual Q over the infinite trace, they must occur equally often. Let that settle in. It might not be true. We can sample a 10,000 trace of just 10,000 finite elements. It might not be true that P and Q occur equally often there, but over the infinite trace, this is the same as saying, which is why it's called fairness, that they occur equally infinitely often. Yes, is there a question?
So is the, I don't want to say inverse, that's not the term I'm looking for, but could you switch the terms and it means the same thing in this case?
Very good. It does. Okay, so if you switch GF, if you rewrite this as, does this is equivalent to GFQ implies GFP. It's the same thing because we're talking about infinite traces. Okay, so this was, I think I already gave you this example. Invariant is this idea of expressing that you want something to always hold. And more often than not, it is like a safety property for your system, right? So you can interpret in English that something bad will not happen. That's when you want to use G of not happening, okay? That's what the invariant is for. And I gave you this reactor example already, that always the reactor temperature must not, it looks like go above 1,000 degrees. Another example is something called liveness. Liveness is this notion that something good will happen. And so, eventually you will all become rich is a liveness property. And the trait of the liveness property is that you would see eventual operators in liveness properties. These are, again, just high-level categorizations because we develop these properties for different systems all the time. And just like, in systems theory, we have equivalent capacitance and resistances. Here, people have categorized the type of properties they see consistently occurring in different systems, right? So eventually, X will be greater than 5. Always, it must be the case that when something starts, it will eventually terminate. Something good will, will happen is a liveness property. Fairness, we've seen, always eventually something implies always eventually something else. So let's look at the statement in red. If something is attempted infinitely often, it will be successful infinitely often. That's how you specify that always eventually when a process is ready to run, it will get infinitely often, it will get a chance to actually execute. Right, so this is where we started today with these ideas of how can we express requirements which are in plain English and have ambiguous terms more formally, more in a non-ambiguous way. And so the way to do that is through linear temporal logic. So now you have both the ingredients you need to do model checking. You have a mathematical description of a transition system. You know what are these things called traces and paths and words. And now you know how do you actually specify a requirement in LTL. So let's do a quick exercise. I've just for your reference shown you what the definition of LTL is. So let's quickly see which one of these are valid LTL formulas. So this shouldn't take much time, but we can go for it. So is this a valid LTL formula? Not negation of phi 1. Is this allowed? Yes, it is allowed because you can think of this as a LTL which is valid. What about the second one? Negation of phi 1 until phi 2. This is not allowed. This is not a valid expression because when you use until, it must be of this form. And that does not satisfy here. And the last one, always not of phi 1 or not of phi 1. That's allowed, okay? Because or is a valid LTL, even though it's not part of the main dictionary, but it can be derived from negation and therefore not of phi 1 or not of phi 2 is valid, and globally is also valid. We did this manually last time, whether this was true or false. But now I want a LTL formula for each one of these expressions. So let's start with the first one. How can we say that M holds true eventually? How do we specify this in LTL? M is true eventually. Fm, okay? Not P, it's M. So Fm is that M holds true eventually. What's the next one? Always M holds true eventually. Okay, I'll write this one for you. So GFM, because we just added the always in front. M is always followed by a Q. Let's do both interpretations. One where M is always eventually followed by Q, and the other where it's next followed by Q. Give me both the expressions. So what's the LTL formula for M is always eventually followed by Q? M, F, Q. Is this a valid LTL formula? But you're missing one symbol. Implies. Yeah, I know what you meant, but this is what you meant. M implies FQ, which means M is eventually followed by Q. And so similarly, you can say M implies XQ, which would be the other interpretation of the same statement. But there's a always, so we may want to do this. And what's the last one? P holds continuously before F holds. How would you say this in LTL? P holds before F holds. Yeah, this is I thought the most straightforward one. P until F. When F holds, P must hold continuously until that point. Questions on this? Yeah, so we just did all of those. And previously, we've already seen that none of them were satisfied by our transition system, right? So all of them we have expressed in LTL, and we know why they are not satisfied. We did that in the previous lecture where you actually gave me counter examples of traces. How will you specify I will be back, okay? Eventually back. So this is a chance for you to contribute to next year's lecture, okay? I've been doing this every year. I ask for whatever have you. They keep changing from classic movie titles to dialogues to memes. So you feel free to contribute those on Piazza, and I will include it into the slide deck next year as your sort of batch of 2019 LTL specification. Let's keep going. I have a lot of these. There is no spoon. Always no spoon. That's a LTL formula of Neo's dialogue. I don't even know if you are old enough to know what reference this is from, but even the text says we'll always have Paris, so always have Paris or always Paris. Very simple. Let's look at a more tricky one. I'm going to make him an offer he can't refuse. Next offer implies cannot refuse. Okay? I'm making him an offer means I'm going to do that next, and that implies that it cannot be refused. You cannot hide from me. I will find you and I will kill you. So cannot hide and I will find you implies eventually I'm going to kill you. That's the plot of the entire movie in a LTL formula. So next time we have both the ingredients of what a transition system is and what is a LTL formula. We'll put those together to do model checking. This cloud thing that we haven't discussed yet, but I've promised you can give guarantees that something is always true. You know, how will you, if your transition system had more than the states that can fit on a PowerPoint slide, and you had some property, you cannot manually trace, right? The mental cognition will hit its ceiling at some point. So you need algorithms that given a transition system, given an LTL spec, they will automatically give you an answer. And the answer is either yes, this transition system satisfies this spec, which means all traces from this transition system satisfy this spec or LTL formula. Or if that's not the case, the model checking tool will produce a counterexample where there will be a trace where the formula is violated. And it will hold true for infinite traces of your model. That's the power of model checking. Once again, on Piazza, do contribute. That's how my list of these LTL specs will grow. But we will start looking at model checking in the next lecture onwards. Okay, we can stop here.